9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Pressurization start. X plus 8, 9, 10, 11, 12, 13.
The United States was in the space business along with the Russians, and Explorer 1 was the beginning.
In January of 1958, the United States launched Explorer 1, their first artificial Earth satellite, catching up with the earlier Soviet Sputnik 1 and Sputnik 2. Since then, thousands upon thousands of artificial Earth satellites have been launched and operated in the vicinity of the Earth. And now we even have satellites around other planets, asteroids, and the Sun. The concept of a satellite, the concept of orbital motion in the gravitational influence of a planet or other body, is fundamental to our subject. And so we're going to get fairly deeply into it. We're going to find out how to calculate the parameters, the key quantities of an orbit. And we're going to figure out how we might change orbit using rocket propulsion. Let's start with some terminology. We'll be talking about a satellite in orbit around a planet. Now, the planet is very large, and its gravitational pull is what causes the satellite to move in its curved orbital path. And the satellite is very much smaller than the planet. And really, fundamentally, that's the distinction. The satellite is small, the planet is very large. And so, although we'll be using the term planet and satellite, those things might mean different things in different contexts.
Let's consider some orbital systems to see how this works out. In one of the Gemini missions of the 1960s, 2 astronauts orbited in a spacecraft, the satellite, about the Earth, the planet. So far, so good. But also, the same laws of orbits apply to natural satellites. For example, we can have a planet Jupiter with a satellite, its moon Europa. But also, the same laws of orbits will apply to the solar system. In this case, we might have a planet orbiting the sun. So now the sun is what we're calling a planet, and the planet is what we're calling a satellite. To understand the laws of orbits, we need to review the concept of energy. So let's review it. We're going to be talking about the specific energy of a planet moving around the sun. It's the sum of 2 parts, the kinetic energy. Kinetic specific energy is 1/2 v squared. And then minus gm over r, where m is the planet's mass, is the potential energy, the specific energy. And this is useful in all kinds of ways. For example, we saw how we could use this to figure out the maximum height above the surface, or the maximum radius that a sounding rocket launched vertically would achieve. And that sounding rocket has an energy which is total energy which is less than 0. The negative potential energy dominates, and so it can only get to a certain maximum radius from the center of the planet. But if the rocket is given a speed equal to the escape speed or greater, which is the square root of 2 times the circular speed, then it can actually escape the planet altogether. And then the total energy is positive, and when the rocket is a great distance away, the only energy it has is kinetic energy.
The laws of orbital motion were first worked out in the early 17th century by Johannes Kepler. Kepler was interested in finding out the laws governing the motions of planets around the sun, but they're the same laws for all satellites. Then later, at the end of the 17th century, Isaac Newton showed how Kepler's laws of orbital motion emerge from the laws of motion and universal gravitation that he was able to figure out.
Kepler's first law is about the shape of orbits. Now, we're familiar with circular orbits, but Kepler says that in general, the orbit of a satellite is an ellipse, a sort of flattened circle, and the planet is located not in the center of the ellipse, but at one of the two focus points of the ellipse. Now, if we're talking about an ellipse, there are really two quantities that kind of define the ellipse that we're talking about. And the first one is called the semi-major axis. Now, the long diameter of the ellipse is called the major axis, and the semi-major axis is half of that. It has the relation to the major axis that the radius has to the diameter. So the long length of the ellipse is 2 times a, the semi-major axis. And then there's the parameter that tells you the shape of the ellipse, how flattened is the circle, and that's called the eccentricity of the ellipse. A circle has an eccentricity 0, and if you have a really long, narrow ellipse, the eccentricity is a number near to 1. For an ellipse, the eccentricity is always between 0 and 1. Let's consider that orbital shape a little more closely. Since the planet is off-center in the ellipse, there will be one point over here on the left-hand side of the diagram, which is the point farthest from the planet. It's called the apocenter distance. The apocenter is also called, if the planet happens to be the Earth, the apogee, or if it's the Moon, the apoLune, or if it's the Jupiter, it's the apogee, believe it or not, and if it's the Sun, it's the aphelion. It's the apo whatever. And then there's another point on the opposite side of the orbit where the satellite is closest to the planet, and that's called the pericenter, or perigee, or perilune, or perigove, or perihelion. It's the closest point. And the key thing to remember is that the sum of these two, the apocenter plus the pericenter distance, is equal to 2 times the semi-major axis. Now the eccentricity relates these nearest and farthest distances to the semi-major axis. So for example, the apocenter is 1 plus the eccentricity times the semi-major axis. And the pericenter is 1 minus the eccentricity times the semi-major axis. We can express that relationship in a different algebraic way by writing a formula for the eccentricity. The eccentricity is 1 minus the pericenter distance over the semi-major axis. The pericenter is always less than the semi-major axis, but suppose it's equal to the semi-major axis. Then the orbit would be circular, and this would tell me that the eccentricity is 1 minus 1, which is 0. Kepler's next law is about how the planet moves along its orbit, or the satellite in our language. How does the satellite move along the orbit? Kepler realized that it didn't move at a constant speed. Sometimes it was faster and sometimes it was slower. And he managed to formulate a beautiful geometrical rule, which was quite correct. And he said if you drew a line between the planet and the satellite, that line would sweep out equal areas in equal times. So that means that when the satellite is very close, near its pericenter, then it will have to be moving very fast because that line is short. But if it's far away near its apocenter, then the satellite will be moving more slowly because that line from the center of the planet to the satellite is much longer. Equal areas in equal times. The law of equal areas gives us a nice relation between the speeds of the satellite at pericenter and apocenter. So suppose we have a nice orbit. It has an eccentricity of about 1/2, in which the apocenter distance is 3 times the pericenter distance. Then, because the apocenter is 3 times farther away, the satellite must be moving 3 times more slowly. In other words, the pericenter radius times the pericenter speed is equal to the apocenter radius times the apocenter speed. And that's a relationship that is sometimes very useful indeed.
Kepler then formulated a third law, but it took him almost a decade to discover it. The first law is about the shape of each orbit, and the second law is about the motion of a satellite on its orbit. The third law allows you to relate the speeds of satellites in different orbits. And it's a little bit trickier.
So here's Kepler's third law, what he called the harmonic law. Let's suppose you have a planet with several satellites orbiting it in different orbits. Then, for these orbits, the cube of the semi-major axis of each orbit is proportional to the square of the orbital period. Now that's quite a mouthful. Qualitatively, it means that larger orbits take longer. The orbital period, the amount of time it takes to make one complete orbit, is longer. But the relationship is not linear. The relationship looks like this, that the cube of the semi-major axis, A, is equal to some constant times the square of the orbital period, P. And that constant may depend on which planet we're talking about. So let's take a look at how this works out for the solar system. The planets are satellites of the sun, so to speak, and so we can write down their semi-major axes in what are called astronomical units. Those are units of distance where the Earth's orbital radius is 1, and we'll write down the orbital period in days. And then we'll just calculate the ratio a cubed over p squared. And we see that even though some orbits are many times larger than others, and some orbital periods are many, many times larger than others, that ratio is the same for all of the planets in the solar system, all of the satellites of our sun.
We've actually seen this law before in the special context of circular orbits as a relationship between that orbital period and the radius of the circular orbit, which is, of course, the semi-major axis of that orbit.
By looking at how Newton's laws of motion and of gravitation apply to a satellite in orbit around a planet, we found for a circular orbit that g, the gravitational constant, times m, the mass of the planet, over 4 pi squared, times p squared, where p is the period of the orbit, was equal to r cubed, where r is the radius of the orbit. And of course, we also notice that r is the same thing as a, the semi-major axis, for a circular orbit. And so that means we know the value of the constant for Kepler's third law. And we might call this the Newton-Kepler 1, 2, 3 law, because it tells us that mass to the first power times orbital period to the second power is proportional to semi-major axis to the third power. And that's true not just for circular orbits, but for all orbits. And as we've seen, that's really useful. For example, if we see a distant planet with a satellite orbiting it, we can determine the mass of that planet simply by observing the orbital period and the semi-major axis of the satellite.
Now, armed with our understanding of Kepler's laws and our knowledge of the mechanics of ballistic motion, we're ready to begin the subject of orbital mechanics. And orbital mechanics is based on one key idea, that geometric information about the shape of the orbit, whether it's a circle or an ellipse, what its semi-major axis is, what its eccentricity is, that geometric information is related to mechanical information. That is, information about motion, about force, about energy.
And here's the most important and most useful mathematical relation that expresses this. It says that the specific energy, the total specific mechanical energy of the satellite, both kinetic and potential, is related to the semi-major axis A of the orbit. The size of the orbit is related to the energy. And we can express this in two ways. One is we can say that the specific energy is minus gm over 2a, negative, of course, for a bound orbit. Or we can just algebraically manipulate this and say that a is equal to minus gm over 2e. If we know something about the energy of the satellite, we know something about its orbit. If we know something about its orbit, we know something about its energy.
That's a lot of mathematics. And even if we have the ability to consult a sheet of useful equations, it's still easy to get lost in all of the mathematical relationships that we have presented and to figure out how to apply them. It's, as I said before, it's like a game of chess. It's fairly easy to understand the rules of chess, which pieces can move in which ways. But what's much harder to understand is why you should make a particular move at a particular time. The rules simply set the rules. They don't tell you how to play the game. So our challenge is to figure out how to use all of these mathematical relationships to play the game of orbital mechanics and calculate useful information about the motion of a satellite about a planet. So we'll do this by working out a fairly detailed, fairly elaborate example.
So here's the situation. We imagine that we have a satellite orbiting the Earth, and that at a certain time, the satellite is 1,000 kilometers, that's 10 to the 6th meters, above the Earth's surface, and it's moving horizontally at a speed of 9,000 meters per second. So we've given mechanical information about the initial motion of the satellite. And our job is to find out everything we possibly can about the orbit that this satellite will follow in the future. We need a little information to get us started. For example, we need to know that quantity g times the mass of the Earth, which is about 4 times 10 to the 14th in MKS units. And we need to remember the radius of the Earth, which is about 6,370 kilometers, because the distance that matters for the satellite is not its altitude above the surface, but its distance from the Earth's center. Now, a satellite at that radius would have a circular orbit speed that we can calculate. It's 7,350 meters per second. But the speed of our satellite is 9,000 meters per second, which is greater than that. And so that tells us two things. First, the orbit is not circular, but is elliptical. And second, because we're going faster than the circular orbit speed, we're beginning at perigee, the point of closest approach to the Earth. And that means that we know the radius of the satellite's orbit at perigee and the speed of the satellite at perigee. That's a good start. Now it's time to plan our next move. There are lots of things we might want to know about the satellite. We might want to know its radius and speed at some point on its orbit. We might want to know the total mechanical specific energy. That's going to be the same at every point on the orbit. We might want to know the semi-major axis or the eccentricity for the orbit, or the orbital period. We might want to know the radius and the speed at apogee, just as we already know the radius and speed at perigee. So there are lots of equations that relate all these things together. I've written down a whole bunch of them, and this is something I might have on a sheet of equations or something. And the question is, how do I decide what equations to use when? How do I decide what pieces to move at what time in the game? And so here's what we need to do. The first thing is we want to look for equations that relate what we know to what we want to know. So for example, if we find an equation where we know everything except one quantity, then we can solve the equation for that quantity and find what it is. And of course, to do that, we'll want to first do algebra. We'll want to derive an algebraic expression and then plug in the numbers in a calculator to figure out what the answer is. To make sure we're doing it right, we want to make sure that everything is in a consistent system of units, the meters, kilograms, and seconds units. The orbital period will be in seconds. The semi-major axis will be in meters, and the specific energy will be in joules per kilogram. All right, so let's take a look at what we know and what we might want to know. The first thing we notice is that we know the speed and the radius at one point in the orbit. That is to say, the starting point, which we've already determined, is the perigee. And that means we can calculate the specific mechanical energy, the energy E, 1/2 v squared minus gm over r, because we know everything except that quantity. And so that's the energy at every point on the orbit, because the energy is conserved. And so that will let us then calculate the semi-major axis of the orbit, because in the equation for semi-major axis, we know everything except the semi-major axis. So we're going to start with energy. So here we go. The energy, of course, is the same everywhere in the orbit, so we can compute it at the perigee point that we know all about. And so we take the speed at perihelion squared times 1/2, and we subtract off g times the mass of the Earth over the radius at perihelion, and that comes out to minus 1.35 times 10 to the 7th joules per kilogram. That is the total specific mechanical energy of the orbit. And once we have this piece of information, we can compute the size of the orbit. That is to say, we can compute the semi-major axis. We know that the semi-major axis is equal to minus gm over 2 times e. And so we can substitute the values in, making sure to keep everything in meters, kilograms, and seconds, and we wind up with 1.474 times 10 to the 7th meters, or about 14,740 kilometers. We know the semi-major axis of our satellite's orbit. So where do we go from here? Let's go back to our list of equations and take a look. There are more equations where we know everything but one quantity. For example, in the lower left, we note that we know the perigee radius and we know the semi-major axis, so we can find the apogee radius. And once we find the apogee radius, we can also find the speed at apogee from the equation we got from Kepler's second law. And here's how that equation works out. The apogee radius is twice the semi-major axis minus the perigee radius, which is 22,110 kilometers. That happens to be about 3 times the perigee radius, and so that means that the apogee speed is 1/3 the perigee speed, or 3,000 meters per second. Now we're in a position to calculate some more things. For example, from the perigee radius and the semi-major axis, we can find the eccentricity. And also from the semi-major axis, we can calculate the orbital period. Let's do that. The eccentricity is 0.5, being 1 minus rp over a. And the orbital period we can get by taking the square root of something we get from the Newton-Kepler 1, 2, 3 law, and we find out that it's 17,820 seconds. And for convenience, we can now convert that to hours. That's just under 5 hours. So now we've calculated about everything there is to calculate about the orbit. We have determined its size, its shape. We've determined how fast the satellite is moving at the point of closest approach to the Earth and the point farthest away from the Earth. And we've calculated the overall orbital period. Now we did this in a particular order, but the order doesn't matter. At each stage, we simply looked around for equations in which we knew everything but one variable, and then we calculated that. And in the end, we knew everything from just the 2 pieces of information, the initial radius from the Earth and the initial speed at the perigee point. And we don't have to stop there. There are more things about the motion of the satellite on the orbit that we can calculate given the information that we have. Here's an example of what I mean. Since the perigee distance from the center of the Earth is around 7,000 kilometers, and the apogee distance is around 22,000 kilometers, then somewhere in between, I don't know exactly where, the satellite must be 10,000 kilometers away from the center of the Earth. At that point, how fast is the satellite moving? Well, we can figure this out using the concept of energy, because the total specific energy of the satellite is the same everywhere on the orbit. And so we know that the specific kinetic energy there is that total energy, whose value we know, minus the potential specific energy, which is plus gm over r. So let's work it out. The kinetic energy is minus 1.35 times 10 to the 7th joules per kilogram, and we have to add 4 times 10 to the 14th over 10 to the 7th joules per kilogram. That 10 to the 7th is the 10,000 kilometers, 10 to the 7th meters. And we get that the kinetic energy, the specific kinetic energy, is 2.63 times 10 to the 7th joules per kilogram. And from that we can determine that the speed at that point is 7,250 meters per second. That's slower than the perigee speed of 9,000 meters per second, but it's faster than the apogee speed of 3,000 meters per second.
Okay, it's a long road that we've traveled in this particular example. But notice that we only started out with a couple of pieces of information. All we knew was the initial distance of the satellite from the center of the planet and its initial velocity. And we knew the mass of the planet. And from that, we were able to determine everything about the orbit: its energy, its semi-major axis, its eccentricity, its apogee, everything. So that's I think a good indication of the real power of the mathematical formulas that we've developed. But of course, we still have to learn how to play the game, how to move the pieces and when to move which pieces in order to get what we want. And the key idea there is simply take mathematical relations in which you know everything except one thing and calculate it, and keep going. So next time we're going to talk about orbits that are not ellipses. These are orbits that are not really orbits in the sense of going around, but the trajectory of an object passing a planet or escaping from a planet is described by a different kind of curve. But a lot of the equations we found and a lot of the relationships that we found still hold good. And then we'll talk about using rocket propulsion to make changes in orbits and how we can calculate the fuel required to go from here to there. Okay, that's all to come. We'll see you then.